Our previous video saw us taking a look at Taylor series and using MATLAB to be able to find a Taylor series for any sort of function. I believe we used the transcendental function. In this video, we're going to take a look at how we can try to utilize MATLAB or leverage it to be able to really investigate what's going on with these sorts of Taylor series. So in our example, we're going to write some MATLAB code to find polynomial series to represent f of x equals sine x, and the orders are going to be 5, 10, 15, and 20 for the polynomials. We're going to plot the polynomial and the original function on the same graph, and we're going to use the subplot function. All right, so we're going to use some sims, and I'm going to say x, and then I'm going to name my polynomials p5, p10, p15, and p20 for my different polynomials of the orders. And I'm going to say that p5 is going to be equal to Taylor. And if you remember the commands, we're going to have the original function, and I forgot to define the function. So I'm going to say fun is going to be equal to sine of x. And we're going to say that p5 is going to be equal to fun. And remember, we define the parameter order. And in this case, it's going to be 5. Right? And the good news is, once we have that, we're just going to copy and paste that. Right? So this is going to be P10, this will be P15, and this will be P20. And then, of course, we have to change that third parameter inside of the command. All right. So now we're going to go ahead and we're going to start being able to graph these. And remember, we're asked to use the subplot function. Now I'm just going to use one to start out with. So you might remember you use the subplot, and then there's 3 parameters. So we're going to have 1, 4, which means that we have 1 by 4. And then we're going to have 1, means the first position. On the same graph, I'm going to easy plot our function. I'm going to call that fun. And then also what I'm going to do is I'm going to use the hold, and I'm going to also easy plot P5. And I'm going to run this once we're done. I'm not going to put any labels on it, and we're going to hold off. All right, now let's run this just to see what we get. And it might take a moment because of the graph. And hopefully I didn't make any syntax errors. Still working. We know it's working because there's a pause up here. It might just be taking a while because it's the first time I've run it today. So please be patient. Sorry. While that's going on, I'm going to copy and paste the rest of these, because what we're going to do is we're just going to change a few of the parameters to be able to get the rest. And as if on command, it came up. All right, so this is what we get. This is our 5th degree polynomial. All right, and it's in one position. And notice that around 0, we have a pretty decent representation of the sine function. All right, but then our polynomial, notice it's a 3rd order polynomial. Not sure why it doesn't give us the 5th degree, but so it gives us that cubic. And unfortunately, it's just going to go ahead and not really model it too well, looking like after maybe 3 or something like that. Okay, so let's go ahead and we're just going to change a few parameters. So I'm going to say 142, and instead of 5, I'm going to plot 10, and I'm going to say 143, and I'm going to plot P15, and then finally 144, and I'm going to plot P20. All right, now we're going to get an array of the graphs. And what we notice is that with each iteration, right, we end up with a little bit better representation of the sine function. So the blue curve is the sine function, and the orange one is the polynomial. So notice in the second graph, it starts becoming pretty good. All right, so like it looks like right around, like maybe right around 3.7 and negative 3.7, it starts to have a little divergence. Now over here, it's really good. And then in this 20th degree polynomial, and this one's basically overlapping one another. All right, so that's the use of the polynomials, these Taylor and Maclaurin polynomials, is to represent these transcendental functions using polynomials rather than utilizing transcendentals. All right, now the last section we're going to take a look at is we're going to take a look at differential equations and how we can use MATLAB to solve differentials. There's a number of commands that we can use, and I just put some basic code in here. I realize that differential equations is not a prerequisite to this course, so some of you may not have taken differentials or may be taking it at this time. So I'm just going to show you how to utilize MATLAB to solve some really basic differential equations. When you do take differentials, hopefully your instructor shows you how to use MATLAB to solve a little bit higher level sort of workings with MATLAB. And so all we're going to do is we're just going to do two examples. We're going to write MATLAB code to solve y prime plus y is equal to x. And this is the initial condition, y at 0 is equal to 1. And then we're going to solve this second order non-homogeneous differential because it's 2x plus 3, not 0. And we have the initial conditions that the derivative at 0 is 1 and the original function at 0 is 2. All right, so first thing we're going to do is we're going to define a few sims. And I'm going to define an x, and I'm going to define a y at x. I'm going to start by defining the differential equation. So if I say EQU, and you might remember the original differential was y prime plus y is equal to x. All right, so right here. So wherever you see y prime, you're just going to make that derivative of y with respect to x. And in MATLAB, that's the function diff y comma x. Right, so this is going to be diff y comma x plus y is going to be equal, and I'm going to say double equal to x. Right? Now we're going to have conditions. So the condition is going to be that y at 0 is going to be equal to 1. All right, and where do we get that from? Well, if you look back, remember right here, y at 0 was equal to 1. So that's our initial condition. And then now we're going to use our dsolve function. Okay, so I'm going to call solution 1. That's going to be equal to dsolve. All right, so that's our function differential solver. EQU, which I defined as right here, and then condition. Right. And I'm just going to go ahead and run this just to show you what happens with this. It might take a moment. Right? But we get this solution, x plus 2e to the minus x minus 1. Right? And what we could do is we could do an fprintf to say the solution to, let's just say percent, well, I'll just say the solution to the DE is percent S. And I'm going to use sol1 as the final parameter here. And of course, we could plot the solution too. So if you wanted to, you could do an easy plot. And I'm not saying that I asked you to do this, but just in case you wanted to see what the solution looks like, there you go. So you can run it. And sometimes in differential equations, we look for the long-term behavior, right? You might remember, for those of you that have taken it, a lot of times differential equations model rates of change. And the original function, you might be able to find some sort of long-standing position. So for instance, what happens to the voltage after a long-term time t? All right, this is the sort of thing you might need the graph for. So it never hurts to look at the graph, and that's how you guys can use it. All right, so a second order differential. So our last example that we're looking at in this section, we have y double prime minus 6y prime. Let me bring this up. Minus y is going to be equal to 2x plus 3, and two initial conditions, y at 0, y prime at 0 is 1, and y at 0 is 2. All right, so when we do this, now we're going to have this second order differential equation. So this just means the second derivative, which is diff y comma x comma 2 when we program that in MATLAB. All right, so I'm going to say that the new equation is going to be equal to diff y comma x comma 2 minus 6 times diff y comma x, and then it was, I believe it was minus y. Yeah, minus y equals 2x plus 3. All right, so that's our equation. And I need double equals back here. All right, now our conditions, all right, so we're going to have, and we're going to have an array of conditions. So I'm going to need the brackets to indicate that there's more than one condition. So we're going to say y at 0 is going to be equal to 2. And that's the easy one, right? But then we also have the derivative, all right? And what I'm going to do is I'm going to define dy, just to make this really easy. I'm going to say dy is going to be equal to diff y comma x. Right, so I could have really just said dy right here if I would have done that before, but that's okay, no big deal. So I'm going to say that dy at 0 is going to be equal to our 1. And I'll close those. Okay, so now we have our conditions, right? And I'm going to bracket that out. We don't need it. Right? And finally, let's just call sol2. That's going to be equal to our dsol. And just like we did before, we're going to have the equation and we're going to have the conditions. Okay? And just like we did before, we can go ahead and just say the solution to the DE, and I'm just going to change this to sol2. All right, so let's go ahead and run this, see what we get. And this should be a double equal. All right, so we run. All right, and here's our solution. All right, and for those of you that have taken differential equations, you probably remember that solving non-homogeneous differentials gets pretty ugly because you have both a particular solution as well as a complementary solution. All right, so it's expected that this is going to be a pretty ugly looking solution, which it is. All right, again, if you want to graph it, just to kind of see what this monster looks like, we might as well. Let's see what we get out of this. And again, I didn't ask you to graph it, but it never hurts to see what the graph of the function looks like. This one has a very sharp exponential increase, whereas the previous had a very sharp exponential decrease. Right. So that's going to conclude our look at how to utilize MATLAB to work with the Sims functions. And hopefully this can help you in your other classes, like your calculus and differential equations courses, to be able to check your solutions.